So I will talk about matching networks, and this is a very common problem in RF engineering. So I just sketch now a quadrupole. So this is a so-called quadrupole, and I will say I consider here a lossless matching network. This is a lossless matching network, and the purpose is, for example, that we have an arbitrary load impedance here. For example, it could be the impedance of an antenna. For example, I want to use, for example, a 50 ohm system to transmit power to a certain antenna. And of course, then we must here consider our generator. So I call this U0, for example. And of course the generator normally will have a real generator impedance, RG, which we assume that this will be equal to the characteristic impedance of a transmission line, or in most cases in RF engineering this is 50 ohm. So we will now assume that we have a generator which has an internal resistance of 50 ohm, and we want to transmit now as much energy or power as possible to our load impedance. Of course, it's always, if you have, for example, a transmitter in RF engineering, then you want to get the maximum power out of it. Or if you have a receiving antenna, and then you would have here, for example, the input stage of a receiving amplifier, then also the receiving amplifier will have a 50 ohm input impedance, and then you want to get the maximum out of the antenna. So in both cases, the principle is that we now have to match this complex load impedance to this internal resistance of our generator or our RF source. So, and if I talk about matching now, what does this mean? For example, the question is now under which circumstances I really have a matching, or what must I see as input resistance into the lossless matching network so that I really have a matching? Can somebody answer this question?
Sorry, can you
Pardon?
can you specify your question? I don't understand it clearly.
You don't understand it clearly, yeah. Then I try to understand why I draw a simpler picture. So, say if I have here a source, a voltage source, you know all that I hope it's still clear, yeah, so I have a voltage source, and you know that in the easiest case we can assume that I have a voltage source with a certain internal resistance I call here Rg. This I say that this is the internal resistance of our voltage source. And I have here, for example, the case that I have here an arbitrary load resistant. And my question is now, how do you have to choose the load resistance to get the maximum power out of your source? This is a common question from in the lecture of basics of engineering. Who can answer this question?
We choose RL to be equal to Rg.
This is correct. So we choose RL equal to Rg, then I can get the maximum out of my source here. And this we call, in principle, matching. So if I translate this question or this situation to this, what value must the input impedance have? So we will operate at a certain frequency F naught here, of course. So our circuit will really have or operate at a certain frequency, say, for example, 100 megahertz. So what must be the property then of the input impedance I see into my matching network at this frequency? Now you already solved this problem, so you can now also tell me how to solve this problem, or not to solve, but what must be the property of the input impedance then?
Equal to Z log.
At F naught. So the value must be what?
Must equal to Z log.
To Z naught. No, it must be equal to Rg, or which I call also here ZC. Yeah? Under these circumstances we have a matching here. Did this become clear, or are there still some questions? There are no questions now? Good. Then it seems to be clear. Good. Then I will go on. I will delete this. And what I now want to do is to translate this question into our Smith chart. So I will here sketch a crude Smith chart now. Perhaps I just do it like this. So here almost here. I must do this. So I will just draw one circle here. And the other circles I will just draw with that, sketch it with the hand, just so this is our one circle. You will see that this one circle is very important. Here in the center of the Smith chart we have a 1, and here we have the imaginary part circle of 1 and the imaginary part circle of -1. So this is now our Smith chart. Here you have the 0, the short circuit point. Here we have infinity, here we have J, and here we have -J. So this is our Smith chart, and of course now we have our load impedance here. I told you that this load impedance, it shows a complex value. This is why I have to draw an underline. And of course this load impedance, what do we know about the load impedance? If I want to draw it into the Smith chart,
reflection coefficient at the load, right?
So I want to say we don't know nothing about the load impedance, or not very much about the load impedance. We only know that the load impedance here is somewhere, the normalized load impedance I can somewhere draw into the Smith chart, like this. Maybe here we will have the normalized load impedance. I have a certain, if I consider, for example, a certain antenna at F0, then somewhere in the Smith chart we have a load impedance line. And then you see, what must the lossless matching network do? You see that we at a certain frequency, F0, I want to see here into this matching network the generator impedance or the ZC, the 50, in most cases 50 ohm, or the characteristic impedance. So where does this point lie in our Smith chart? If I want to have matching in the input.
At the origin, at the center of the Smith chart.
At the center of the Smith chart, this is correct. So this is here, and we call this a matching point in our Smith chart. This is our matching point, and you see what must now our matching network do. Our matching network must somehow transform our load impedance at a certain frequency into our matching network, into our matching point. This is the purpose of our lossless matching network. The matching network must somehow constructed that this load impedance for a certain frequency is transferred into or transformed into the matching point. Is this more or less clear, or Or do you understand what I'm talking about? Good. So I hope this did become clear now, or almost clear. And now, of course, at the moment we don't know how this matching network looks like. So in the next step I want to explain some simple matching network which can realize this, or realize the problem here, or solve the problem. And now we come to the essential part eigentlich of dealing with the Smith chart. Because with the Smith chart we are able to design or to find the values of certain matching networks. So a simple matching network could look like this. Or right here, simple a simple matching network could look like this, that I have a transmission line where we assume that this transmission line is almost lossless. So this transmission line is described by ZC and beta here. And at the moment we assume that we can change the length of this transmission line. And then we assume here to have the load, a certain load impedance. And we assume to have here a series element So this is a lumped element. This means it's not low. Here we have a transmission line, and here we have a lumped element Jx. So if x is positive, we will have a series inductance or series inductance, and if x is negative, we will have a capacitance. So, and I want to, what we have to do now is to think of how we can use these elements to find a matching. This means at a certain frequency, set in at F naught must be equal to set C, or must be equal to 50 ohm in the most cases. Then we would have a matching. And if we consider this, then we have to make us familiar how we can walk, I call it walk, in the Smith chart using these elements. So to make this more clear, I again sketched two simple Smith charts here. example, this one. So this is our simple Smith chart here. One, again the unit circle here, and here this lines. So I think of this to be our Smith chart, and now of course we already know, or we remember that the load impedance can lie anywhere in the Smith chart here. Could lie here, could lie here, or yeah, for example here. And now I want to discuss with you what will be the influence of the transmission line here. If I connect the transmission line in front of the Smith chart, what will be its influence? What I ask you, what will be the influence on the transmission line if I change the length at a certain frequency, for example? Can somebody tell me? So, as I told you in the lecture already, a transmission line, if I say here or in, this is our input reflection coefficient. Of course, you see here ZL will reside in certain output reflection coefficient, RL. This is our RL. And we know we are here, the Smith chart, we are in the plane of the reflection coefficient, and we know that Rin is equal to RL times the exponential function of minus J2 times beta L. And what did I tell you about this factor? What does this factor do with the reflection coefficient? It may be here, or here. Who remembers?
It turns clockwise.
It will turn our reflection coefficient in clockwise direction. That means with the help of the transmission line, I can walk in clockwise direction in the Smith chart. Perhaps to make this more clear, I just draw some simple circuit here. So if I would connect now my transmission line to this point, I can walk somehow on this circle in this direction. Or if I would have this one here, oh, just it's a little bit more complicated. So I can walk then on this circle here. It's a little bit more complicated. So we can always walk on a circle around our 1 point. So we can walk on a circle with constant RL absolute value. So I call it walk. With the absolute value of RL constant, this means we can walk on circles around the origin of our Smith chart. Is this more or less clear, or are there some questions? So then I delete this here again. Well, of course, you see, with the help of only the transmission line, you can never come into the matching point. So we need a further element. And I draw again a Smith chart here. Example this. Here is our Smith chart. The line here, we have the point 1. I don't have any. And again, I draw the Smith chart here. So here we have a line like this. Here we have the point 1. Maybe I draw here some further line. Circles, real part circles. For example, one real part circle would look like this. This is a real part circle. And now I assume that I'm already here or into this this corresponds to set in prime in principle. It corresponds to a certain input impedance, and of course this input impedance, this is the input impedance I see into this into the transmission line at this place. For example, if this set in would lie on this circle, on this read part circle, if I use an inductance, for example, in which direction I will walk now, or move, in which direction I can move by inserting a positive real part. You see now, for the input set in, we would have, this is Jx plus set in prime. So we have here a series connected element. This is connected in series to the transmission line. It has no physical length, so it's 0 here because it's a lumped element. But what can I change now with the help of this reactance? Can somebody explain? Or so if I add to a certain, or to any set in prime reactance, what will be changed?
You mean what will be changed on the Smith chart?
Yeah. Or where do we walk in the Smith chart?
We will change the imaginary part circle. Like we move to another different imaginary part, right?
We move to a different imaginary part, but we do not change the real part. This means we can move now, for example, in this direction, or walk in this direction with an inductance. So if I would use, or perhaps I sketch it like this, so if I use the series inductance, I would move in this direction. And if I use, for example, a capacitance, of course a capacitance is negative, then we will move in this direction. So we can, with the help of the reactance, we can move on a circle with constant real part, or we can walk. We can walk on a real part circle. So with the reactance, we can walk onto a real part circle. So we walk in this direction to positive imaginary parts. If I put an inductance in front and I move in negative direction, if I put a capacitance in series to our transmission line. Yeah. Are there some questions again to this, or? So there are no further questions. So what we have to do now is, in principle, to combine the two movements to move from this point into the one point. And I just want to sketch this, or give you in principle a step process to do this now. So to explain this, I just delete this and I again sketch a Smith chart. So again, my Smith chart here. This is our Smith chart again, yeah. Here you have the 1, infinity, here you have a 0. So this is our crude Smith chart again. And now I assume that our, for example, our load impedance is here. This will be our load impedance, and so we already know that the goal is to come here. This is our matching point. And the question is now, how can we combine the two possible movements to come from here to here? So, so the first step is very easy, of course. First, draw set L, the normalized load admittance in to the Smith chart. So that means I just draw in this cross here in the Smith chart. So this will be the first step. And now we are able to put in front of this load impedance a transmission line. And with the help of the transmission line we can walk on which circle again? Who can tell me? On which circle we can walk with the help of the transmission line?
The circle caused by the exponential minus beta.
Yeah. You are from the mathematical point, you are right, but we can walk on a circle around the origin of our Smith chart. So we can use in principle our compass to do this walking. So I will do a tick line. We can walk in this direction here. All over. So the question is, if I want to come into this point, and I have as a further element, I have this reactance. Where do I have to walk to come to be able to go into this point? Somebody an idea?
Sorry, could you repeat your question?
So again, if we have a transmission line like this, we can walk on a circle around the origin of our Smith chart. This is quite clear. The longer the transmission line, the more we can walk on this circle. So we can walk everywhere. But our goal is to come with the next element to come into this point here. And this with this point we can just change the reactive value or the imaginary value. And the question is, where must we walk to be able to come into this point?
So, oh, you mean what kind of reactance should we add to make it move to the origin, right?
Yeah, we have two possibilities. You have the possibility to use a positive reactance. This means you use an inductance, or you must use a capacitor. Then you use a negative reactance. But as a result, I want to be here. So perhaps I can ask you again. So you see here, if I say these are normalized impedances, so we want to be here, so one must be somehow Jx plus, and we know that we cannot change the real part, so we must already here have the real part plus J something x in prime. So from this is clear, though you must always use a negative of this. If you use a negative of this, then you come into the one point. This again results in the fact that you must walk onto the one circle. So there are always two possibilities to walk on the one circle. You can walk on the one circle with positive imaginary parts. There are positive imaginary parts. Then you must use a capacitance here. So with the help of the capacitance, you could walk then down this line into the one circle. Here you must use a capacitance in this case, and if you walk to this point, then you can use an inductance to come into the one circle. So the second step would be draw into the Swiss chart with the help of the inductance, you can walk onto the one circle. And if you walk to the inductive part of the one circle, you must use a capacitor, or you must walk on the capacitive part of the one circle, then you use an capacitance, an inductance here. So sorry, I did not sketch this here, so here you must use an inductance. So we can further say here that so normally this element is given, so if you have an inductive reactance transform to the capacitive one circle. So if you have an capacitive reactance, then transform to the inductive one circle. So this is now the second step. You see, with the help of this simple matching network, we can always find a matching. So if we, of course it depends on where you start and which element you have in front. So the first step is always draw the normalized impedance into the Smith chart, and in the second step you somehow, or you use the transmission line to transform onto the one circle. And if you use a capacitor in front, it means if you have a capacitive reactance, then you must transform to the inductive part of the one circle. Here in the upper plane we have the inductive part of the one circle, and if you have an inductive reactance, then you must transform to the capacitive part of the one circle. So did this become clear now, or are there some questions? So then I want to give you a task, and you can try to solve this task up to for our next meeting. So I delete this. So the task will be now that we have a matching network. So I say we have here a transmission line. And I guess here we have the load impedance, and I assume that the load impedance is equal to 100 plus J 200 ohm. This is our load impedance, and of course the ZC will be 50 ohm. Our frequency of operation F0 will be 150 ohm. And we use a capacitor in series to the transmission line. And the question is how to choose the length of this transmission line and how to choose the value of the capacitor so that you have the input impedance that in at F0 is 50 ohm. So this would be, or this is a task you can try to solve up to our next meeting. You have to do is to figure out the length of the transmission line and the value of the capacitor if it shall operate at 150, oh, not ohm, sorry. Of course here it must be written megahertz. Of course this would be the wrong unit for frequency. So I want to have the matching at 150 megahertz, and yeah, this would be the task for you to solve now.